So today, oh, got out the quiz. Nobody's going to remind me about the quiz. Get out your piece of paper. Got one question. Wait for the professor to stop giving you the answers before I put it up here. Okay. One question, multiple choice. Just put your answer in your name, click. No talking. What's the answer?
Molecular.
B. How do you know? It does not have a metal in it. So the video only talked about 2 of those 4. Which 2 did it talk about? Ionic and molecular. And how do you tell the difference between them? Ionic compounds have a metal in them.
Isn't elemental just 2 elements?
That's not even.
Fire.
I think this is where the video left off. So, one way that the ionic compounds and molecular compounds are different is that how they behave when you put them in water. Okay? When you put an ionic compound in water, it breaks apart. When you put salt in water, it is no longer sodium chloride. This is sodium chloride solid. You put it in the water, and we get this sodium ion and a chlorine ion, and they have AQ, meaning aqueous, which is dissolved in water. So at that point, that sodium ion is completely separate from that chlorine ion. They are not together. They don't know that they were ever together. They're completely independent of each other, floating around in the water. Molecular compounds don't do that. This is molecular compound dissolved in water. This is just oxygen, O2, okay, 2 oxygens together, dissolve it in water, and it stays O2. The O's do not break apart. This is methanol. If we put methanol in water, it just becomes methanol aqueous. It goes from liquid methanol to aqueous methanol. Because there's no metal in it, it's not ionic, and if it's not ionic, it will not break up. Things break up into ions. And if it didn't start as individual ions that came together, it can't break back up easily. So we're going to go back and talk about these ionic compounds more. Most of what we're going to do in this class deals with ionic compounds because they do the most, and also they make up the biggest chunk of the periodic table, because a good, maybe 80% of the periodic table is metals. And any compound that has a metal is going to be ionic. When we talk about ionic compounds, we talk about being made of ions. And there are two different types of ions. There are monatomic ions and polyatomic ions. The ones we've talked about so far are monoatomic ions, or just monatomic ions. They are just one atom that gained or lost electrons to gain a charge. They can be positive, they can be negative, but they're just single atoms. And those atoms gained or lost those electrons because, remember, they wanted 8 valence electrons. They wanted to become like our noble gases all the way on the right. And this is going to trick people up for the rest of the semester. We'll talk about it more later on. But transition metals, these ones in the middle, there are a few of them that can actually have multiple different charges. It depends on the situation they're in. Whereas everything else is set. We said everything in the first column becomes +1. And these are +2, -1, -2, -3. For the most part, these are +2, but there are some weird ones that we'll look at. So these are some really common monatomic ions. Look at the names and see if you can find a pattern.
The negative ones are ides.
The negative ones are ides. You got negative oxide, negative nitride, chloride, fluoride. So all the negative ones, you basically took the element oxygen, took the first syllable of it, and added I. Nitrogen, nitride, chloride, fluoride. What about the positive ones? Think simply, even simpler than that. It's just the element name, right? Sodium ion, and the ion that comes from sodium is sodium ion. Aluminum ion, magnesium ion, and potassium ion. When you're naming the ions, if it's a cation, if it's a metal, just say the element name, put the word ion after it. And so we have molybdenum ion, or chromium ion. And like we said, with the negative ones, if it's a non-metal, just kind of take the first syllable of the element and add the I onto it. So this would be bromide or sulfide. These are the ions that you're going to see the most. Doesn't mean these are the only ones you're going to see, but these are the ones that you're going to see over and over and over again. They make really good quiz and exam questions because they're easy. I try to avoid these because they're tricky. The opposite, or the counterpart to the monatomic ions, is the polyatomic ion. A polyatomic ion is an ion that consists of a group of atoms. And they are always in that group. Once they form that group, they will not break apart. So this is sulfide. This is just sulfur that gained 2 electrons to become sulfide. But we have a polyatomic ion called sulfite. This is SO3 with a 2- charge. Sulfite is always SO3 2-, and SO3 2- is always sulfite. Sulfate is SO4 2-. What's the difference between these three? Just the number of oxygens. But there's still ions. This says no oxygens. Here we have 3, here we have 4. That's an ion, that's 1 ion, and that's 1 ion. It's a monatomic, and then 2 polyatomic ions. That charge doesn't belong to any specific atom in that ion. It is overall on the entire thing. And this SO3 will never, ever break apart. Oxoanions are polyatomic ions that have oxygen in them. That's not a definition I would worry about. So here are some polyatomic ions in their names. Do you see a pattern here?
The negatives don't, all of them don't end with I anymore.
They're negatives and they don't end with I. So we can't just follow that same rule again. Look at nitrate and nitrite. What's the difference between these two? There's one oxygen different. Which one has more oxygen?
The higher the oxygen has 8.
The one with the higher number of oxygen has 8. The one with the lower number has I. There's 4 sulfate, 3 sulfite, 3, 8, 2 I. And so the 8, the suffix 8, doesn't correspond to a certain number of oxygens. Whether you have an ion with a nitrogen or a sulfur or a chlorine, there's always sort of a reference point. And that reference point has been decided to be the reference point. And that one is 8. So for the nitrogen oxoanion, we have nitrate, NO3 minus is nitrate. You take one oxygen off, and it becomes nitrite. Sulfate, sulfite, chlorate, chlorite. These are common polyatomic ions. The slides that you printed out, are these already blocked off for you? Mm-hmm. Okay. So I blocked off the ones that you're never ever going to see, because I don't think. I left the ones that you are going to see, but you only are responsible for memorizing the ones that have asterisks next to them. So there's, wait, no. Yes, sorry. There's a later slide where you have to memorize the ones with the asterisk. This one is, don't memorize the ones with it. And so you'll have this to refer to when you're doing the homework, in case you run across these weird ones, because the book or Wiley Plus may throw them at you. I won't throw them at you. And so you won't need these in a situation where you don't have this. But these other ones, you do have to memorize. And there's a lot of them up there. But if you remember that 8ith rule, you can memorize a lot fewer than are up here. Because I personally remember nitrate is NO3. And if I remember that nitrate is NO3 minus, then nitrite must be NO2 minus. I don't have to memorize nitrite. I don't have to memorize chloride or sulfite. Because I remember which one is the 8. So you'll need these memorized for the exam. So what does an ionic compound that has polyatomic ion look like? You write it the exact same way that you would write something like sodium chloride. But when you look at it, hopefully at some point you'll start to see that that CO3 is a polyatomic ion. This calcium is clearly a metal, so it's a cation. It's a positively charged ion here. And so everything else must be negatively charged anion. And if we go back and look at our table, yes, carbonate is CO3, 2 minus. So it looks the same. And the way you pronounce it is you say the metal, calcium, and and then you just say the polyatomic ion name. You don't have to worry about changing it. It's just calcium carbonate. That's calcium, that's carbonate, so together it's calcium carbonate. This is sodium, and HCO3 as a whole is bicarbonate. Sodium, cyanide. So it's sodium cyanide. And then potassium nitrate. Does this make sense? This isn't hard, right? Just say the two names. There is only one polyatomic cation that you're going to see, and that is ammonium. Don't get ammonium mixed up with ammonia. Ammonium ion is NH4+. Ammonia is NH3. So remember that ammonium is NH4 positive. And you can take the polyatomic cation with a polyatomic anion and make something that looks like that. So if you see that, you're going to have to be able to recognize that NH4 is one of those polyatomic ions, and that NO3 is nitrate. So that when you look at that, you can see where is that division. The division falls here. That's one ion, and that's another. Ionic compounds fit together really nicely. They're in very ordered arrangement of atoms. So this is sodium chloride. The green ones are chlorine, the white ones are sodium. They're arranged one by one by one so that there's a sodium and a chlorine, a sodium and a chlorine. When we look at the formula of an ionic compound, what we're really looking at is the ratio of one element to the other. Ionic compounds don't actually exist in a molecule. Sodium chloride is not a molecule. It's an ionic compound. That means that there is one sodium and then there's one chlorine, but that's just a ratio. You can have two sodiums and two chlorines. In a giant block of sodium chloride, you may have 5 billion sodiums and 5 billion chlorines. This sodium is no more attached to that chlorine than it is that one, that one, that one, or the one behind it, or the one that would be up here.
Only, sorry, I didn't mean to cut you like that. Only when you put them in the aqueous solution, that's when they change.
Correct.
The.
So this is solid form. So it's not dissolved in water. In this case, they are being held together by their opposites attract positive and negative forces. When you put it in water, this chlorine is going to go that way, that one will go that way, the sodiums will go all over the place, and they don't have anything to do with each other at that point. If you have a polyatomic ion, it works exactly the same. Here we have calciums, and then these giant CO3 carbonate ions, but there's still one of these for every one of those. It's a little harder to see because it's messy, but it's still 1 to 1. Another way we talk about compounds, and this is not a truly important slide, but we need to talk about it, is just based on the number of different elements that are in the compound. And this is really easy. A binary compound, bi meaning 2, has 2 different elements in it. A tertiary compound has 3 different. There's lithium, nitrogen, and oxygen. It doesn't matter that this is nitrate. It doesn't matter that there's 2 ions. All that matters is that 1 element, 2 elements, 3 elements. And a quaternary compound has 4. Even though this is ammonium carbonate, it's nitrogen, hydrogen, carbon, and oxygen. That's 4 different elements. That's a quaternary compound. So the tricky part, when we get to these ionic compounds, and what's going to cause you the headache, is writing formulas for them. In sodium chloride, the chlorine has a negative charge, the sodium has a positive charge. You put them together, and your overall charge is 0. Because you have a positive and a negative, they basically cancel each other out, and you have 0 charge. When you write the formula for an ionic compound, those charges have to cancel out. If they don't cancel out, your formula isn't correct. And remember, an ionic compound, the formula that you're writing is just a ratio. It is not actually counting how many are in a molecule. And so you want the simplest ratio possible. It's like reducing a fraction, simplifying a fraction. I can say that there are 2 sodiums and 2 chlorines. That's still 1 to 1. But you can simplify 2 and 2 down to 1 and 1. So in an ionic compound, if you can simplify the subscripts, you have to. Okay. So when we write a formula, we have to make sure that the total positive charge, when you combine it with the total negative charge, equals 0. Meaning that the total positive charge is equal to the total negative charge. Right? And there's actually a simple way for us to do that. Okay? This is sodium chloride. This is +1 and -1. If we just have one of these and one of those, it automatically cancels out to 0. This is calcium. It's a +2 charge. Nitrate has a -1 charge. So, because the calcium has a +2 charge, and the nitrate has a -1 charge, we need 2 of these to get to a total of -2. So that we can have -2, which cancels out +2. We kind of flip it around, so we have sulfate with a -2, and sodium with a +1. Again, we have 1 and 2, so we need 2 of these to get +2 equal this -2. If we take the number of ions, multiply it by the charge on that ion, we get the total charge. There's barium chloride, and then here starts to get trickier. This is barium. Barium has a 2+ charge. This is phosphate. Phosphate has a 3- charge. So, if I have 1 and 1, I have +2 and -3. I need more pluses. But if I add another barium, I'm going to have +4 and -3. So it's still not balanced. So now I need more minuses. So I add another minus. Now I have 4 and 6. I'm still not balanced. So I need another barium. Once you do that, now you have 6 and 6. But you don't want to be doing that in your head every time. You don't want to think, if I add one of these, now I'm not balanced, so I now have to add one of these, and then I have to go back and add one of these. There's a simpler way to do it. If we look at an ionic compound, and we think about it as the 2 ions that it started as. So sodium chloride starts as a sodium ion and a chlorine ion. There are these charges here, right? Because they are 1s, the 1s are assumed. Don't forget that this is actually 1+ and 1-. What we're going to do is we're going to take this charge, just the absolute value of it, so the 1, and we're going to move it down, and it's going to become the subscript on the chlorine. Then I'm going to take the 1 that's on the chlorine, move it down, and it's going to become the subscript on the sodium. So what I end up with is Na1Cl1. That 1 came from there, that 1 came from there. But we don't write 1s in formulas. So we erase it, and it's just sodium chloride. If we go to the next one, we have calcium. Calcium 2 plus, and it's combining with nitrate 1 minus. I'm going to take that 2, move it over here, take this 1, and move it over here. So I get Ca1, NO3, but I got to put this 2 here. If I put a 2 there, does that look right? No, that looks like NO32. So this 2 applies to NO3. It doesn't apply to the nitrogen or the oxygen. It applies to NO3. So I'm going to put NO3 in parentheses, and then the 2 goes on the outside. So that's telling me that there are 2 of what's inside the parentheses, which in this case is 2 nitrates. So if we go to that last one, the harder one, I've got barium 2 plus and phosphate 3 minus. We don't have to go through all of that logic stuff. All we have to do is swap numbers. And when I do that, I get Ba3, PO4, 2. And we got the same result. When you do this, make sure when you swap the numbers that you can't simplify it any further. We look at, there's no example up here. So let's look at barium oxide. We've got 2 and 2, so if we swap the numbers, we're going to get Ba2O2. But that can be simplified. So Ba2O2 is not a correct answer for this problem. You have to simplify it. If you simplify it, they both become 1s. We don't write 1s, and so it's just BaO. So I've got calcium and nitrite, and it wants us to write the name, to write the formula for the ionic compound that you get from calcium ion and nitride ion. So the first thing we have to do is we have to write out the 2 different ions that we're dealing with. What is calcium ion? What's the charge on calcium ion? 2 plus. Then the other one is nitride. What is the symbol for nitride? Nitride is just a nitrogen ion. It's not one of those polyatomics. Nitride is just nitrogen, and nitrogen forms a -3 charge. So, if those are the 2 ions that I'm starting with, what's my final formula going to be?
Ca3N2?
Yes. We got Ca. The subscript on the Ca is the charge on the end. Ca3, N, the subscript on the end comes from there. Ca3N2. What is my total positive charge? I have 3 of these calciums. Each one is +2, so what's my total positive? 6. What's my total negative? I have 2 nitrogens. Each one is -3. -6. So I have +6, -6. They're equal, so it cancels out. So it's correct. What about barium nitrate? We've got barium. What's the charge on a barium ion? 2 plus. And nitrate. Do you remember what nitrate was? Nitrate was the NO3. So you haven't had time to memorize that. No worries. Nitrate was NO3 minus. So what is my final formula going to look like, do you think?
three in parentheses.
I've got BA what?
Parentheses.
It's just positive.
No.
No.
Three.
Where is the subscript coming
Three.
from?
One.
Oh,
we-
just leave it.
Yeah, leave it blank.
Right. It's the one from here, we don't write ones, so we don't have to write a subscript. BA NO3, now what?
Now you put those in parentheses.
Right, because this 2 is going to be here, I have to put NO3 in parentheses. So we have 1 barium and 2 nitrates. Potassium with a charge on potassium.
Oh, the 3 is just for the oxygen
Yes.
alone. It's
The
not
3
the-
is just on the oxygen.
Okay.
The 2 goes to everything. So there's actually 2 nitrogens and 6 oxygens. What's the charge on potassium? Positive 1. And sulfate. Sulfate, SO4, 2 minus. That was on that table. So what's my final formula? K2,
Parentheses.
don't need it.
Oh, you don't need it.
So you got K2, K2, SO4, and then there's a 1. Some people are much more comfortable always writing parentheses around polyatomic ion. It's not technically correct, but you're not going to get marked wrong for it. So if you feel comfortable putting that polyatomic ion in parentheses, do it. Okay? That's going to help you remember that that is its own thing. Because later on in the semester, we're going to start dissolving these and doing reactions with them. And if you don't remember that SO4 stays SO4 and doesn't break apart, you're going to have trouble. And if you get in the habit of putting it in parentheses, that's going to be a reminder to you that this is its own thing. Don't break it up. Got a bunch of examples here. Calcium and fluorine. What is the formula for the compound from calcium and fluoride? Go.
CA and then leave that blank. And then fluoride would be 2.
Right. You got Ca, calcium, you got Ca, then you got to figure out the subscript on the calcium. The subscript on the calcium is the charge on the fluoride. Fluoride is a -1 charge. So the calcium is going to have a 1 subscript. Then you get to the fluorine. You write F, then you have to figure out the subscript on the F. The subscript on the F is the charge from the calcium. The calcium gives you a +2 charge. So you end up with Ca F2. What about aluminum and oxide? Yeah, go
I
ahead.
just have a question. Wouldn't fluorine have a 2 already on it or no? Because it's fluoride?
It's diatomic only when it's on its own, just when it's fluorine. When you're, is that what you're getting to?
Yeah.
Right. When you're talking about ions, it's not just fluorine. And so you can never have that. You can have that, or you can have that. But you can't have
So
that.
fluoride is the ion and fluorine is the diatomic.
Correct. Correct. Aluminum and oxide. Yeah.
So for today's question, would you just say like A, just put A, or would you put the charges?
You'll have to figure out the charges. And so I could very well ask you, what is the formula for what you get from calcium ion and fluoride ion? And then you would have to figure out the charges on those two things. What do I get from aluminum and oxide? Al, well, we got aluminum and oxide. So we have ALO, we have to fill in the subscripts. What's the subscript on the aluminum? 2. It's the charge from the oxygen. Oxygen forms a -2 charge, so we have Al2. What's the subscript on the oxygen? 3. That's the charge from the aluminum. Aluminum is here, and we said this column forms a 3+ charge. So it's Al2O3 came from up there. Let's do E. Ammonium ion and phosphate ion. Do you remember what ammonium ion is? NH4 plus. NH4 plus. And then phosphate ion was PO what? 4 charge? 3 minus. And so what is my final formula? NH4 3. How am I going to write that? NH4 3 PO4. If that 1 comes here, don't have to write it. If you want to put that in parentheses, you can, but you don't need to.
What's the ammonia? Is that NH3?
NH3. Got this? You're going to be naming compounds for the rest of the semester. So if you don't get it, make sure you get it. Yeah?
I'm still a little confused about the subscript.
Okay. Let's do C. So we've got sodium ion. Yeah, Na+. Are you comfortable with that? Okay. Because it's in the first column, it's +1. Right. And then we have sulfate ion. Sulfate ion is on that chart. You can't just look up here. That's one you're going to have memorized.
Not the negative.
That is SO4 2 minus. You'll have it by next week. You just got it. So we've got Na+ and SO4 2 minus. So when we write our final formula, I'm going to write Na, the sodium, then we have to figure out what the subscript on the Na is. It is the charge on the SO4. And so that charge comes here. This charge is going to come down here. So we get Na2 SO4 1. SO4, you got SO4 with the sulfate, and then the subscript on it is 1, because the charge on the sodium is 1. And so what we really have is that. Na2 SO4 1. But because of convention, we don't write 1s, and so that 1 gets erased, and then technically those don't have to be there either.
Okay, that makes sense. Thank you.
Would the, sorry if this is a dumb question, but would the transition metals be +2 charge?
Almost all of them are. We're coming to that. Pretty much all of them are +2. Got it? The homework that goes with this lecture used to be a lot of work. I don't remember how Wiley formatted it, so we'll see together. It's supposed to be a lot of work. It's not hard work, it's repetition. Okay? If you keep naming things wrong, you're going to get a lot of things wrong the rest of the semester. So you need to learn to name things correctly. So like I was saying, the polyatomic ions, when you dissolve them, they don't break up any further. So this was our dissolving of sodium chloride. The sodium came over here, the chloride went over there. But if you dissolve something with a polyatomic ion, that polyatomic ion stays together. So this is potassium sulfate. When you dissolve that, there are two potassium ions there. They are completely independent of each other. So when you dissolve it, one potassium can go over here, the other can go over there. There are two of them. There are two potassium ions. That's what that's saying. So the thing we're looking at is potassium ions, and there are two of them. We call this a coefficient. We're going to deal with that a lot once we really start getting into our reaction. So we get two of these, because it's K2, and then we get one sulfate ion. The SO4 is a unit. It does not break up any further. SO4, 2 minus. So remember, when you dissolve something in water, it has polyatomic ions. The polyatomic ions don't break up. So if I put that into water, what am I going to get? I'm going to get NH4 plus, and I'm going to get 3 of them. Because it's now dissolved in water, it's aqueous. And what else am I going to get? And I'm going to get 1 of these phosphates. So we already talked about how to name the ions. Naming the compound is just putting them together. And so when you need to, if you look at a formula, you have to think about which ions came together to make that. So if you look at that, that was a sodium and a chloride. And so it's called sodium chloride. This was sodium and a nitrite, so you get sodium nitrite. Here we have MgCl2, but that 2 is only there because magnesium has a 2 plus charge. And so what came together was magnesium ions and chloride ions, so it's magnesium chloride. All you have to do is take the 2 names of the ions and say them one after the other. The metal, that cation, the positively charged ion, comes first, the negatively charged ion comes second. So what would you name that? Aluminum oxide. So aluminum, remember the metals, you just say the element name, and this is oxygen ion with oxide. You completely ignore the charges, or not the charges, ignore the subscripts. So aluminum oxide. It's assumed that if you tell someone you have aluminum oxide, they know how to balance the charges by switching the numbers, and then they can figure out that aluminum oxide is Al2O3. So you don't tell them it's Al2O3, you just say aluminum oxide.
What does the I imply?
That is a negative ion that came from an element. So what's that called? Sodium chloride. Sodium, that was nitrite. Magnesium chloride. Magnesium nitrate. Barium oxide. Lithium nitride. Nitride is just the nitrogen element turned into an ion. Here's a flow chart. Flow charts don't mean anything to me. I include them in case they mean something to you. Okay, so now we get to those nasty transition methods. this throws a wrench in the whole thing. Because if I tell you to give me the formula for sodium chloride, it is always NaCl. If I tell you to give me the formula for the compound that gets made between aluminum and oxygen, it is always Al2O3. But if I tell you to give me the compound that you get between copper and oxygen, you can get two different ones. There is no set answer. So if you look at these two, what is the difference between them?
More oxygen substrate.
Two atoms of copper.
Right. This one has one copper. That one has two coppers. Thinking about what we were doing here, why do you think that here we have one copper and there we have two? So oxygen is 2 minus, right? But oxygen is always 2 minus.
Copper's a transition.
Copper's a transition metal. And so you're on the right track. It has to do with the charges here. If oxygen is always 2 minus, and copper is a transition metal that I said can act kind of weird, what do you think happens to the charge of copper? It can change. It's either going to be 1 or 2. Okay? So let's take those formulas and break them apart to figure out what we started at. We have CuO. What's the subscript here? It's 1, right? And that 1 came from up here, which means we started with O1 minus. What's the subscript here? 1. That came from up here, which means we started with copper 1 plus. But something should jump out at you here as being wrong. What did I say about oxygen? It's always 2 minus. So what do you think happened? Why is it 1 minus here?
Did it steal an electron?
It reduced. They're both.
The copper.
They should both be like 2.
Right.
It should be 2 minus.
It got simplified. So if oxygen is always 2, you know that had to have been 2 minus. There's no other choice. But if that was 2 minus, that means we doubled that one. If that one got simplified, this one got simplified also. So this one must have been 2 plus to start with. So in this case, we start with copper with a 2 plus charge and oxygen with a 2 minus charge. If we look at the other one, Cu2O. This means we started with Cu and O. Subscript here is 2. That 2 came from up here, remember. And so the charge on the oxygen was 2 minus. But subscript here is what? 1. And that came from up here. Now, oxygen is already correct. This one did not get simplified. So in this case, copper was 1 plus. So you can look at that. You can look at the formula that they're given, and you can backtrack, work backwards, and figure out what the charge on that copper must have been. So there are a few elements that are weird. There are more than are on this table, but the only one that's not up here that you're going to need to know is silver. Okay, and I'll get to silver in a minute. So iron comes in 2 flavors, 2 positive and 3 positive. Copper comes in 1 positive and 2 positive. And then here, tin is shown as 2 positive, but it can be other things. When we write the name of an ionic compound with one of these weird elements, we have to write what charge that metal had in this compound. So if I write iron 2 chloride. That means I have iron with a 2+ charge. And you write the 2 in Roman numerals. Here's iron 3 chloride. That means the iron had a 3+. Copper 1, copper 2, tin 2. Don't forget that those Roman numerals tell you the charge on that metal. A question that I'm going to ask you over and over and over again this semester, and some of you are going to get it wrong over and over and over again this semester, is what is the name of that? Or what is the name of that? What is the name of that? What is the name of that? Copper 2 oxide. Remember to work backwards and figure out what the charge on that copper was. And that tells you what number the Roman numeral should be. What is the name of this one? Copper 1 oxide. Because we had to work backwards and figure out what the charge on that copper was. You're going to be very, very tempted to say copper 2 oxide. But it's not correct. You have to work backwards and figure out what the charge is. I guarantee you, on the exam, one of these two will be on there saying what is the name of it. And then, in the cumulative homework assignments that we're going to have, one of these two are going to be on there. And even at the end of the semester, people are going to get it wrong. Yeah.
Are the parentheses necessary in there?
Yes.
Can you explain it one more time so we don't get it wrong?
The Roman numerals in the parentheses tell you the charge on that metal. They do not tell you the subscript on it. They tell you the charge. So if I write copper sulfate, okay? I didn't say copper 1, right? It's copper and sulfate. When you write the name down, you're going to have to tell me, is it copper 1 or copper 2? Otherwise, it's going to be wrong. If you just say copper sulfate, that's wrong. So you have to work backwards and figure out what the charge on this copper was. So how do you want to do that? How do you know it's 2?
Well, because you were saying earlier we have to work reversed. And if I'm reversing that, that would mean that was 2 before.
How do you know?
It was given like that.
How do you know it was 2?
I don't
Where
know,
did
I'm
the 2 come
guessing.
from? Guessing is not the key to success.
Okay. I really don't know. That's why I asked you to do it again.
What 2 ions are here? Just ignoring charges, what 2 ions are here?
Copper and salt.
Copper and sulfur, right? What is the subscript on the copper here?
1 right
1,
now.
right? And that came from up here, right? So we're going to put 1 minus there. What is the subscript on sulfate as a whole here?
2. No? As a whole?
As a whole.
2. 1.
The 1. Because it's not written, that means it's assumed. So it's 1. And so if there's a 1 here, it must have come from up here.
Okay.
So I'm going to write 1 plus here. But we know, based on that table, that sulfate is 2 minus, not 1 minus. And so that means this must have been simplified. So that had to have been 2 minus. If that got simplified, this got simplified also.
Okay.
So if these are the 2 ions we started with, what is the name
copper, yeah, copper 2 sulfate.
Copper 2 sulfate, yeah. Copper 2 sulfate. What if we have this copper chloride? Copper what chloride? Copper 1. There's a 1 here that came from up there. There's a 1 here that came from up there. And chlorine is, in fact, -1, so that this was not simplified. So it's copper 1 chloride.
How do you know the charges of like sulfate, which you,
That was on that table. It's kind of right?
oh, you,
There's no way of getting it off that.
So I see, I guess we do the assumed number and then reverse the,
Correct. So when we were going from name to formula, we were writing the charges and then swapping them down subscripts. Here we know the subscripts. We swap them backwards to charges.
okay.
You just have to be careful and figure out, did this get simplified? But in order to figure that out, you have to be comfortable of what the charges are supposed to be on everything other than the transition metals.
I'm figuring it out.
Okay. Other questions? These are all of the ones that are weird. Okay? But you're only responsible for iron, which comes in 2 and 3, copper, which comes in 1 and 2, and then silver. And silver is always +1. So for you, on quizzes, on exams, on the final, any of the transition metals are +2 unless they are iron, copper, or silver. Okay? It's possible that Wiley's going to throw one of these other ones at you, but they follow the same rules in terms of naming. So if they give you a formula with mercury in it, and they want you to give the Roman numeral, work back, figure out the charge on it, and write the Roman numeral. Okay? It's going to work exactly the same.
Why does mercury have a subscript on the first one?
Because mercury is really, really
Do they consider that?
kind of. You'll never, ever, 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 ever see that anywhere other than this line. So what is the name of that? Manganese oxide. What's in that? Still manganese oxide. So that tells us something's wrong. They can't both be manganese oxide. So this must mean manganese is one of these weird ones. So what's the charge on the manganese there? It's 2. Because it's already balanced with the oxygen, and the oxygen has to have 2 minus, the manganese must be 2 positive. So it's manganese 2 oxide.
Number 1 is manganese 2 oxide?
Yes, manganese 2 oxide. And so then, what about this one? What's this one going to be? Is it? You got a 2 on the oxygen.
So then it's
Right, but using the manganese.
Manganese
4?
oxide. That 2 came from there, right? And that 1 came from there.
Right.
But oxygen can't, is 2, so this got simplified. And so it's actually Mn4 plus, like that. Because we multiplied that by 2 to go from -1 to -2, we had to multiply that one by 2. So this is manganese 4 oxide. What about that one? that copper 1 or copper 2? How many copper 1s?
Two.
Copper 2? How do you know it's copper 2? Sulfate has a 2 minus charge always. And this says that 1 copper perfectly cancels that out. So the copper must be positive 2. We'll skip this one, come down to the iron. Is that iron 2 or iron 3?
Iron 3,
How do you know?
because of 3 on the outside of the.
Correct. This 3 came from there. And so that's iron 3 nitrate. Okay, so we're going to move on from the ionic compounds. We're going to move to molecular compounds. These are much easier. Okay? Unlike ionic compounds, where if you have a combination of sodium and chlorine, it is always 1 for 1. And when we're writing the formula for those, we're just writing the ratio. Sodium chloride does not mean that there's 1 sodium and 1 chlorine. That means there's one sodium for every chlorine. It could be 1 and 1, it could be a billion and a billion. In molecular compounds, we're actually talking about individual molecules. So in this case, we literally are counting the number of each element in that molecule. And so, if we have a molecule made of carbon and oxygen, the ratio between them may be different. In a molecular compound, we have all nonmetals. There are no charges involved here. So we don't have to find a ratio that balances the charges. You can make pretty much any combination that you want. And so we can have CO and CO2. What is CO2? Carbon dioxide. What is CO? Carbon monoxide. Carbon and oxygen in different combinations. And so I can't just say, what is the name of the molecule made from carbon and oxygen? Because there are multiple possibilities. You can make SO2 and SO3. If you combine nitrogen and oxygen, there are a whole bunch of possibilities. So we have to have a naming system that allows us to specify which of these combinations we're looking at. And so we looked at that first. What did you say the name of that was? Carbon monoxide. What did you say the name of that one was? Carbon dioxide. What's the only difference between those two? The prefix on the oxygen. In molecular compounds, we're just going to use prefixes to say how many of them there are. So carbon monoxide, carbon dioxide, carbon tetrachloride. There's another table with all the prefixes on there. But tetra is 4, so this is carbon tetrachloride. Sulfur trioxide. Dinitrogen tetroxide, phosphorus pentafluoride. So these are our prefixes. One is mono, di, tri, tetra, penta, hexa, and hepta. Most of them make sense to you. Mono is 1. That's probably already clicking. Di is 2. Tri, triangle, that's 3. Tetra is a tricky one. That's 4. You're just going to have to memorize that unless you can see a connection that I don't. Penta is 5. Why is that one kind of easy? Pentagon. A pentagon has 5 sides. So penta is 5. Hexa, hexagon. Heptagon, which isn't nearly as common, but you've probably heard of a heptagon being 7-sided. Octa, which is easy, and then nona is 9, and deca, like decade, is 10. So those are your prefixes. You're going to have to know them all, but you already know most of them. if you have a mono on the first element in your molecule, you don't write mono, and you don't say mono. You only write mono if it's on the second element. So, how would you name that? Sulfur dioxide. It's really monosulfur dioxide, but we don't say the mono on the first element. So it's just sulfur dioxide. What that one? Nitrogen trifluoride. So for the first element, we're just saying the element name. Sulfur is nitrogen. For the second one, we're giving it the ide name like we did when it was an ion form. So it's sulfur dioxide, nitrogen trifluoride. What's that one? Tetraphosphorus decaoxide. Sometimes you'll see it shortened to just a decoxide, so you don't have decaoxide. So tetraphosphorus decoxide. Those are the rules. Flowchart number 1. Sulfur trioxide. Sulfur hexafluoride. Dinitrogen. In this case, it's not a mono. So we need to give the prefix for the first one. Dinitrogen. Tetraoxide, which is tetroxide. That one? Carbon monoxide. Monooxide is monoxide. And the last one. What's 5? Pentagon. Phosphorus pentachloride. So these easier than the ionic ones?
Yeah.
Yes. What I see a lot of students do, and once they walk out this door, they forget that the prefixes only go to the molecular compound. You cannot use prefixes in an ionic compound. If there's a metal in your compound, throw the prefixes out the door. Okay? You can't do it. And then, I think there's the last naming slide. There are 3 compounds that would have common names. These have nothing to do with any of the naming rules that we learned. And you have to know the names of these 3 compounds. But you already know one of them. Water is H2O. Ammonia is NH3. What is ammonium? NH4 plus. NH4 positive. Ammonia is NH3 with no charge. And hydrogen peroxide is H2O2. This is a good stopping point for our break. So let's start at 25 after on my watch, which is 12 minutes from
Awesome. Thanks.
Which side?
So that machine is next to us. Actually, this one.
Isotope is a different number. So, carbon 13. So, then this is the mass number. So, the proton plus neutrons. So, it will have gas, 6 protons all of them. And it's also have 7 neutrons. And this one's have 8 neutrons.
Yeah, because
It always is gonna have the same number of protons. It's always gonna be six. Yeah.
oh, so we made it
Yeah. Right, that's the number of neutrons.
but depending on what light it is.
I don't know how it is figure out practice training. Probably like,
It seems like we see. I'm just really numbers
Probably like this.
together right now.
so it would be like the mass number. So it would go as 13, then the elements number of each carbon, and then the number of protons. So you're always gonna write it mass number, and then atomic number, and then element symbol. So this one will be, right, so it'll be, what was it, mass number on top, and then atomic number, and then element symbol. Yeah.
Oh, yeah, I saw.
So like that. And then, so this one will be 14, 6, 6.
Fine.
So it'll be like 35, and then, yeah, 35, 17. But, I don't think you care.
I know, it doesn't, this one is
Yeah.
down.
It's a big one.
Yes, but I think it's
Oh, wait, the, I see, no. I see, I think, I don't know, this is,
It might be the U. I'm not
the U
sure.
over there.
Yeah.
Because that's the, I mean, after that they go up.
Yeah. It's probably the U. Unless there's a V.
Yeah, well, it doesn't matter anyway.
Yeah.
So, this was the goal, this is a max, so you go up.
Well, this one I assume it's the U. It's probably the 92.
Yeah,
And then
that's
U
what I'm
is the
thinking.
U.
So that's what, so the 92 will
So we
go
have
forward, right?
2 more concepts to get through today. And the last one is 1 slide. And so we really got 1 more big one and 1 tiny little one. We talked about naming ionic compounds and molecular compounds. We have to talk about naming acids and bases also. Okay? Acids and bases themselves are going to have their own lecture later on. But we need to know now how to name them. So we have to keep just a little primer on what acids and bases are. Acids and bases are both ionic compounds. They're types of ionic compounds that when you dissolve them in water, because they're ionic compounds, will break up into ions. It's just what ions they make acids and bases special. When you add an acid to water, it makes hydrogen ions. That is what makes an acid an acid. So here we have HCl. Well, how would you name that? it's hydrochloric acid. Going just off the names, the naming rules that we just learned. Hydrogen chloride. So in this case, this is HCl gas. This is not necessarily the acid itself, because the acid is only when it's dissolved in water. So this is technically hydrogen chloride. But when you put it in water, we get hydrogen ion and chloride ion. In the water, it is hydrochloric acid. We'll talk about it again later on, but the H plus that forms doesn't actually exist as H plus. H plus is very, very reactive. It's not going to stick around as H plus. Because it's dissolved in water, it's going to latch on to a water. So if I have H2O, and I add H plus, just combine those formulas. What am I going to get? I get H3O, but that charge is transferred over. So I get H3O plus. So that's where that H3O plus comes from. It's just a water with the H plus attached to it. We call that hydronium ion, but again, that's really from another lecture. Bases, when you dissolve them in water, will react with acids. And when you react an acid with a base, you're always going to get water. So imagine you have the acid. Acid is making H plus. You have to get something from the base. H plus plus something is going to give us water. H2O. What does this have to be? OH. We have one plus. We have one H. We need an extra H and an O. And so this is OH. And we need a charge to cancel out this positive. That must be negative. Bases always have hydroxide ion. Hydroxide ion is one of the ones that was on that table earlier. Hydroxide is OH minus. Bases make hydroxide ion. That's what makes a base a base. So they are ionic compounds, so that when you dissolve them in water, they're going to behave just like the sodium chloride or the potassium phosphate or anything like that. This is HCl gas. Put it in the water, and it breaks up. These are the chloride ions. The H plus ions that were here latched on to waters, so we have the H3O pluses. Bases do the same thing. If you had the sodium hydroxide that was listed for NaOH, if you dissolve that in water, what do you get? You get OH negative, and what? And sodium ion. You're going to get sodium and OH minus. These are the easy bases. They have OH in them to begin with. There is one common difficult base. And again, we'll talk more about it later in the semester, but ammonia is a base. Ammonia, NH3, is a base. When you put ammonia in water, it ionizes. And we end up with OH minuses and NH4 pluses. Basically, one of the hydrogens from the H2O got transferred over to the NH3 to become NH4 plus, and what's left over is OH minus. That is too complicated for you in this lecture. So what you need to get out of this is that bases, when you put them in water, make OH minus hydroxide ions. Acids make H pluses, bases make OH minus. We had oxoanions. we also have oxo acids. And while I said that the oxoanions, that's not a term that you use very often, oxo acids is more common. So an oxo acid is an acid that has a polyatomic ion in it that includes an oxygen. And so if an acid, when you dissolve it, makes an H+, it really doesn't matter what the anion is. The cation is always going to be H+, and the anion is going to be something else. It's more or less a placeholder. It's what holds everything together until you put it in the water. But what that other thing is what's going to determine the name of our acid. So these are 3 oxo acids. What is this polyatomic ion? That's nitrate. Nitrate is going to become nitric acid. What is SO4? Sulfuric. Sorry, sulfate. SO4 is sulfate. That's going to become sulfuric. And CO3 was carbonate. That's going to become carbonic acid. So just like with the polyatomic ion names, there's a trend here. You see the pattern here. There are, well, let me tell you, there are 2 different patterns. The first 4 have one pattern, and then the rest have another pattern. So let's focus on the first 4 separately. Just looking at these 4. Say it again?
Well, they end in IC and they start with hydro.
Right. That is the big thing. They all start with hydro. You see that? None of these other ones do. First 4 start with hydro, and they all end with ick, but a lot of the other ones do also. So that hydro is really what stands out. And so these 4 start with hydro, and none of the other ones do. What's different about the first 4 from the rest?
There's only 2 elements.
There's only 2 elements. Here, the anion is an element. All the other ones, the anions, are polyatomic ions. And so the easy ones are the ones with 2 elements. If you have H and then an element, that's the anion, you're going to say hydro, and then the first syllable of the element, fluor, fluorine, fluor, and then end with ick, and then put acid. So HF is hydrofluoric acid. HCl is hydrochloric, hydroiodic, and hydrosulfuric acid. So what is HBr? Hydrobromic acid. What about, well, I'm running out of options. There aren't that many of them. There aren't that many of them. I've already used them all. The other ones are the harder ones. Okay? So here I've gone through, in this slide, you only need to memorize the ones with the asterisk. And so there's those 2, sulfuric and sulfurous, and then I added nitric and nitrous acid. So the pattern here, we have, let's just look at our sulfuric and nitric. What is the ion here? What is that? Sulfate. Sulfate. What is the ion here? Nitrate. They are both 8 ions. 8 ions that end with ATE become ick acids. Sulfate makes sulfuric acid. Nitrate makes nitric acid. What is the name of that ion? If that's sulfate, what is that? if that's nitrate, what's that? Nitrite. So this is sulfite. This is nitrite. Ite anions become us acids. Nitrite makes nitrous acid. Sulfite makes sulfurous acid. So those are the two you got. Okay. The other ones, essentially what happens is as you change the number of oxygens, then the suffix is going to change. So here we have Cl and oxygen. In this case, there are 3 different ones. You don't have to memorize them. But here, ClO4 is not the 8th ion. ClO3 is actually the 8th. And so that's chlorate, makes chlorate acid. Take 1 oxygen off, that's chlorite. It's chlorus. And then there are actually even extremes going up and down from there. Your trick is to figure out which ion has the ATE at the end. If the ion has ATE at the end, the acid will have ic at the end. If the ion has ite at the end, ITE, the acid will have us, OUS, at the end. So you have 4 acids you need to memorize. But if you remember the rules about naming, you only have to remember 2 of them. I personally remember sulfuric acid and nitric acid. So I know that nitrous acid has 1 fewer oxygens. I remember nitric, and so it's HNO3, so nitrous must be HNO2. I remember sulfuric acid, H2SO4, and so sulfurous acid must be H2SO3. So you can either memorize all 4, or you can learn the rules. Make sense? Flow chart. So what would you name that? Hydrobromic acid. Because it's aqueous, that means it's dissolved in water. So it is in the acid form. So it's hydrobromic acid. This is not one of the polyatomic ions that was on your table. I'm going to tell you that is called selenate. If that is called selenate, when you add the hydrogen on it, what's the acid going to be called? Just selenic.
Because it's more than,
Because it's polyatomic, you don't need the hydro. And so it seems like a little detail that's not going to make a difference. But what's the name of that? Sulfuric acid. What's the name of that? In acid form.
hydrogen sulfate.
Hydrosulfuric acid. Hydro, so because it's just 2 elements, you got hydrosulfuric, just like hydrochloric, hydrosulfuric. You kind of got to go with what makes, so it sounds right. If you put hydrosulfic acid, I would not write you wrong. Okay.
So the top one's sulfuric acid, and the bottom one's hydrosulfuric.
Right. And so that hydro does make a big difference. It tells you that versus that. Because they got to make sure whether you have the hydro, it's supposed to be there, or you don't if you don't. So what is this called? PO3 is phosphite. Phosphorus acid. Because this is phosphite, this becomes phosphorus. What would phosphoric acid formula be? H3PO4. If it's phosphoric, that means the ion must have been phosphate, and an 8 ion has one more oxygen than an 8 ion, so it would be H3PO4.
Going back and trying to memorize.
You ate the bigger. That's
Eight.
what I'm going by. You ate the bigger.
You ate the bigger one.
So we do the sulfuric because they have AQ.
Right. If the AQ tells you it's an acid. And
Okay, AQ says an acid.
if it is a liquid or a gas, which I would not ask you to name one of these things in a liquid or a gas form, that's a trick question. I'm not going to do that.
So when it's AQ, it always ends with sulfur, something ick.
It's going to end with ick, acid. Well, it's going to end in acid. If the ion started with an ite, it's going to be us acid. If the ion started with 8, it's going to be ick acid. If it's just an element, then it's going to be ick acid also. But it's going to start with hydro. Name of that. Hydrochloric acid. Second one. That's one of the ones. Got it.
Nitric? No, nitric acid, yeah.
What was the ion here? What's the name of that ion? NO3. That's nitrate. And so what's the acid? Ick. Nitric acid. So if that is nitrate, what is that? Nitrite. And so what is the acid? Nitrous. And the last one, sulfuric acid. What would sulfurous acid be? H2SO3. So, yes, you got to know the rules, but make sure you know nitric, nitrous, sulfuric, and sulfurous.
So the first one is hydrochloride.
Hydrochloric. Hydrochloric. Last slide, I think. One last thing we got to do with this formula is calculate the molecular weight. We talked about atomic mass earlier. Molecular weight is just the same as atomic mass. It's just now we're dealing with combinations of atoms. Before, if I asked you the atomic mass of boron, you could just look and say boron is 10.81. And now we have combinations. And so we have to calculate the mass of that molecule. Yeah?
When it comes to the mass, do you want us to round up or just leave like it?
Your best bet is to just take the number straight off. So to find the molecular weight, the mass of that molecule, all you have to do is take the mass of each atom that's in that molecule and add it up. And that's the mass of the molecule. So H2, you gotta think about what is in that. H2 is 2 hydrogens. The mass up there tells you the mass of 1 hydrogen. And so all you have to do is take the mass of 1 hydrogen, 1.01, times 2 equals 2.02. And because we're dealing with atoms and molecules, the units are still AMUs, atomic mass units. So, we get NaCl, sodium chloride. How many sodiums are in sodium chloride? 1. How many chlorines? 1. So you're just going to take the mass of sodium times 1 plus this mass of chlorine times 1 and add it together. So the molecular weight of sodium chloride is 58.44. So let's do one last example. Somebody say a non-metal. Fluorine with an F?
Yeah.
Somebody say a number between 1 and infinity.
3.
Boring 3. Somebody say another non-metal.
Neon.
Neon can't form compounds, so which-
Sulfur.
bromine and sulfur. What number's on bromine?
10.
10. Sulfur is 5 times 10 to the 8. Okay. I'm in charge, I get to pick one. So we're going to figure out the molecular weight of that molecule. Okay? Even it's going to be easy. Okay? Just line them up, multiply them, and add them. And so what is the weight of fluorine? You look it up, and it's 19.00. So I go 19.00 times however many there are. Get 3. What is 19 times 3? Somebody has a calculator.
57.
True, yeah. You don't need a calculator. We have 4 safe days. What's the mass of bromine? 79.90. 79.90 times how many? 10 equals 799.0. And then we got sulfur. Sulfur is 32.07 times 5 times 10 to the 8 equals what?
So 50 billion, million.
Why is that
You just do 5 times 30. Yeah, that's
Yeah.
times 10 to the 8.
What's 5 times 32?
160.25.
160.25? 0.25 times 10 to the 8, but we got to move this 2 more. So we got 1.602 times 10 to the 10th. Okay, so now we just add that plus that plus that.
Why move it?
Because I wanted to put it in scientific notation.
Okay. 5 times 10 is 160.2, is that what you said?
1.602 times 10 to the 10.
It's 160.35. That's correct.
160.35. Anyway, you're just going to add the 3 up. And you're going to get a giant number. So define the molecular weight, multiply the mass of that element times however many there are, you get a number, do it for each one, add them up. Easy enough? Easy enough when I don't make it hard? Yeah. Any questions? Okay. So we'll go over